If we got an A+ for just showing up, can you imagine? I'd have tenure already. It's what we call the bare minimum. Okay, we want to do more than the bare minimum. You get a C for showing up. You get an A for all the work you do.
I guess it's understandable.
Yeah, you know, we gotta have expectations of ourselves, right? Okay, if you have personal statements, actually keep them. So if Eduardo's coming, because we'll do a second round of peer review today, so that we can get those out. And then if you have summaries, please turn those in if you haven't already yet.
Put my name on it.
Ideally. And then the date, so we can keep track of this.
I just wasn't able to put it out.
Okay. Would you be able to share?
Yeah, yes.
Yeah. Sorry, someone in the chat. You're probably gonna have to just shout. Oh, not as a joke. Okay. Howdy. Let me make sure that the volume's on here. Yep. Okay, we're good. Okay. So just to point out this little piece here, we'll do another peer review. It says that it has a date, but this is just the date we're doing it. Okay, 10/17. And this will be a peer review for your personal statement, if you have one written. What's that? Again, yeah. So a second look, right? Did they make progress? We'll pass it from the right to the left, so you get a different opinion this time. Make sense? Okay. As we mentioned earlier, this class goes between. Hold on, turn off this now. This class goes between the writing and the data. And so today we'll talk generally about data analysis principles and how we make sure that we understand the data that we're taking, because we all have projects that we're doing. Okay. And we're, doing something in order to understand the world around us. Okay. Have you ever heard of a Poisson distribution?
Yes.
Yes, good. One person online. Okay. So if I want to know, the canonical example that I always use is if I want to know how many people are in line in front of me when I go grocery shopping. You heard this example before? Have I done this before? Okay, good. So let's think about this. Okay, go to the grocery store. How many people are in front? 4. What? 4? Yeah, that's a good number. 4. Okay. So I count once, there's 4 people. Next time I go to the grocery store. Now there's a big line. 8. Okay. Next. 2. Okay. Next. 16.
It's almost.
Okay, well, we're not, don't look for a pattern here. Just give me numbers of people that are in front of me in the grocery store.
16.
I'm not accepting that number. I go to a different line. What about the second line? You already did a number.
5. Maybe
5. One more number. 0. Oh, that was a good day. Ah, very good question. I'm going to the grocery store. 4. Okay, good. So in fact, we can repeat because we're measuring something real, right? So what are the rules here? Can I have half a person? No. No, sir. No matter what your possible thinking is there, you can never have half a person. A person either is a person or isn't. Now, is there a dog in the line? Yes, but it's associated with the person, so it counts as one person because the dog is not purchasing any items. Does that make sense?
Are you implying the dog would be half a person if we counted it?
No, no, I'm implying that it's less than a person. For the purposes of counting. Okay. Not in any other purpose. I obviously have 2 dogs. I care for them more than anything. Okay, so these numbers, they represent some number of people in front of us, right? Does this seem like a realistic distribution of numbers? I would say no. Yeah, I don't think this is very realistic. Well, I just only see one set of repeated numbers. 8. That's a huge outlier. Maybe that's the case. How would we even know? Right? How would we even know? So in fact, one thing that we can do is we can say, here's the first time that we looked, right? This was time 1 that we looked. And we want to understand on average how many people are in front of us at the grocery store. Okay, so the question is, we want to understand something about the world, specifically, how many shoppers get in line before me? Okay, and I'm going to call that lambda. That's a variable. I do not know what this is. Okay, so the first time I go to make the measurement, I find 4 people. Am I confident in my result? Is it always 4? No, I'm not confident. And in fact, I don't even know if I'm going to be confident. Right? Second time I go, 8. I don't know anything about that. Right? Third time I go, 2. Okay, that's less than before. 5, that was close to 4. Thinking about all these numbers. As I go to the grocery store more and more, I am making more and more observations of an unknown variable. I don't know what this variable is. In practice, in real life, we don't know the answer to the thing that we're measuring. That's why we're measuring. Why do we take repeated observations?
To see if you're gonna get more confident in a specific number.
Right. So there's 2 things we want to talk about. There's an underlying number, and there's something else in these numbers. There's the underlying number, and there's something else. Randomness. Yeah, there's a scatter in the numbers. So the scatter we call the standard deviation. Okay, we can talk about the mathematical definition of that in a little while, but we want to understand what this means. This means that if I have a mean of 4 plus minus 4, then I will get all of the numbers that you see there, right? Because 4 minus 4 is 0, good. 4 plus 4, 8, that's also up there. 4 plus 1, I can make that, right? Okay. Can this mean be a non-integer number? Yes, it can. A mean, right? What does a mean mean? An average. So we're going to add up all of our numbers and divide by the number of times that we saw it. And we're not going to do anything about it afterwards. What about this one, the standard deviation? We don't know anything about that yet.
We don't want it to be a non-integer.
We expect it to be a non-integer, right? Okay, so here's 2 examples of data. Okay, and I'm going to build your intuition here. Ready? Okay, that's 1. Okay, it's 2. All right, these are 2 data sets. This is data set B. And this is data set A. And this is the number of observations. So each time I took an observation, and then this was, let's say, number of shoppers. Okay. And so let's say this store, that's favorite grocery store. What's Data Bros? And what's this one? Costco. Of course it's Costco. Okay, all right. So intuitively, we understand something about these data sets, even if we don't have the language for them. So right now we're going to develop the language for them, and then we're going to unpack what they mean mathematically. So which one of these 2 data sets has a higher mean number of people in front of you? Costco. That's always true, right? Yeah, fucking sucks. Okay, which one has the lower mean? And you can just see that, right? How do you see that? Yeah, all of the numbers are down here and all of these numbers are up here. That's obvious. Okay. Which one has a higher standard deviation? Costco. Okay, what does that mean? Standard deviation. More spread out, right? So the points end up wider. Okay, that's all we're talking about here. So here the mean is some line that I can draw through here, and the standard deviation is like that. Okay. In particular, if I look at something that's like this, and I say, how many times did I get 0? Let's say this is 0, this is 1, this is 2, this is 3, this is 4, this is 5. And this is the number of times that I got the number, right? Or the frequency, and put that in. So in our particular example, we got 0 once, right? And then we got 1 0 times. And then we got 2 once. And then we got 3 0 times. And then we, oh, that's the wrong number. And then we got 3 0 times. And then we got 4 twice. And we got 5 once. And then we got 1 8 way out here. Okay. So that's not I don't know what that looks like. That kind of looks bad. But let's do the thing that scientists like to do. Let's connect the lines. Okay. Okay. This is a distribution. And the location that a distribution peaks tends to tell you something about it. The shape of the distribution tells you something about it. In particular, we talked about a Poisson distribution. You may know this name. Where's that from? What? What does that say? That says Poisson, I think. Might not have an extra I, but I think that's right. So the Poisson distribution has some fun properties. It only applies to things that are countable. They have to be able to be integers. And it has to be random. Okay. There's some other rules that we'll talk about later. But generally speaking, you can apply a Poisson process if you assume that those two things are true. They're countable and it's random. So if I roll a dice, is that a Poisson distribution? What?
6 options.
6 options? Not random. It's uniform all the way across. Okay, so let's have a look at it. I have maybe 6 numbers here. Hold on, let's ask. Let's roll a die. All right, 1, 2, 3, 4, 5. Okay. Let's say you get a whole bunch of numbers. Keep rolling that die. The frequency of all of them will be like a flat line. Right? Okay. And you say, well, look at that thing. It doesn't have any curve to it. Uniform across the way. Not a Poisson distribution. Right. Yes, right. Yeah. Okay. So instead, if you think about, let's say we took these observations over and over and over and over. Okay. And we had really good numbers. And we found out that, for example, let's say this is like thousands of times up here. Okay. You get 0 a lot, but more often than not, you don't. And it looks something like this. Okay. This would be an idealized Poisson distribution. The beauty of the Poisson distribution is that the number you're looking for, this one here, that's right there. Okay. And there's a relationship between sigma and lambda that we're going to discover. Okay. If I have 2 distributions, let's say one's like this and one's like that, which has a higher mean?
That's more area.
Let's call this 1. Let's call this 2. 1. Good. Which has a higher standard deviation. Why 1?
Higher frequency.
Yeah. Does that process make sense? So we want to just an intuitive understanding of what these 2 terms mean. Right? Okay. So generally speaking, I'm going to talk about astronomy, but you can use the same information. Okay. So let's say we're making observations of people in a grocery store, or maybe we're making observations of the brightness of a star. You get light in, and you want to know how bright the star really is. Right? Does a star always give off exactly the same amount of brightness? No. Not according to your little CCD. Looks like it twinkles, right? We even have a star about this that we teach children. We have a song about this that we teach children, right? Okay. Did you put that together? Yeah, okay. So twinkle, twinkle, little star indicates the fact that the flux of light that we receive from a star is not constant, even to our eyes. So you take some CCD, you place it, you take a picture of the sky, you take another picture of the sky, you take another picture of the sky, you take another picture of the sky, and you're trying to figure out whether or not we can determine how bright it is, right? That's the question we're asking. Is that a Poisson process?
Yes.
Depends on what we're measuring, right? How do we define brightness? And what is light? Is it a countable number of objects? It's photons, right? And photons are? They're countable. You can count how many photons there are, right? 1, 2, 3, 4, 5. Good. So it's a Poisson process. That would have been garbage if I just talked about it. It wasn't even useful, right? Okay. So in your book, you will see there are some fun little, let's see. There's some discussion about things like read noise and gain. I don't necessarily care about those. We can talk about the characterization of individual CCDs if people are interested. But essentially, what we care about is this right here. Okay. This is the signal to noise ratio. This is section 4.4 in your book. This is the section that, regardless of whether you do physics or you do anything else, is probably the most important section for you to know for any type of data analysis. And this is how we characterize our signal, the thing we're measuring, compared with the noise. What does noise mean, other than just listening to me talk?
Stuff that affects the data that we're collecting, but it's not the data.
Right. Stuff that affects the data that isn't the data. Okay. And it's important to distinguish these because if we're thinking about them in the context of light, what are some sources of light that are not the star? Cities.
Neighboring stars?
What's that?
Neighboring stars?
Yeah, maybe scattered light from another star coming in, contaminating our sample, or a star behind it, messing us up. Okay, these are all sources of noise. Anything else? Atmosphere. Okay, what does the atmosphere do? Okay, specifically. What color is the sky? Blue. So it's scattering light in and out of our field of vision, right? So it's going to add some contributions. It's going to get rid of some contributions. We'll see that in the data analysis that we do today. Okay, so we're going through and we're listing all these potential sources of unwanted signal. Okay. Interestingly enough, one of the most beautiful results of a Poisson distribution, and this is going to be kind of difficult to conceptualize. We can go into this in more detail if folks are interested. So we have this thing signal, we have this thing noise, okay? And there is a relationship between the signal and the noise. People know what it is. Let's say the signal is the number of counts, like 8. How uncertain are we about this 8? Now you walked in and you measured it, right? So you say 0 uncertainty. But according to a Poisson distribution, there is some built-in uncertainty. Yeah. Square root of that number. So for each individual observation, each individual measurement, we can say that the signal to noise ratio, as long as it's a Poisson process, can be written as the number that you counted divided by the square root of the number that you counted. Okay, so let's see if we understand this a little bit better. Okay. If I'm trying to determine this lambda, okay, I take the average of all of those numbers. Those are all of the different times that I saw it. So now each one of those is going to have an uncertainty. Some of those uncertainties are going to be big. Some of those uncertainties are going to be small. Is it better for me to get a bunch of observations of a very big crowd at my Costco or Stater Bros? Or is it better to get a really small crowd? Question makes sense or no?
Yeah.
Ah, okay, good. So there's a one thing that's really important here is that these are the signal to noise on a specific observation. And we haven't even yet talked about how confident we are in our mean. There's a whole nother chapter that we could talk about uncertainties on the mean that we just established. So there's uncertainties associated with taking the original observation. If you only have one observation, your uncertainty is
Not good.
not good, actually. Very high. Because recall that your n, your noise, is the square root of the number that you counted. If you counted 1, your uncertainty is 1. And your signal to noise ratio, 100%. The noise is the same size as the signal in a Poisson distribution. Okay. Now you can count more, right? You can add up more and more observations, and we will see there's a new way to combine these uncertainties. So as I take the average of these numbers, I will also have to take the average of their uncertainties in something that we call quadrature. What do I mean by that? Just think Pythagorean theorem, okay? Instead of adding things 1, 2, 3, 4, 5, adding them together, you add them 1 squared, 2 squared, 3 squared, 4 squared, etc. I mean, those are just random numbers I pulled out of my hat. And then you take the square root. And that gives you an estimate for the total uncertainty. Okay. That makes sense? Now I'm just shoving data analysis down your throat. So I promise that we'll get to the data in a few seconds. Okay. So one other thing we want to think about is there are two different there's two different distributions here, right? And we already said that this one, A, Stater Bros, represents the lower mean and a lower uncertainty. Okay. So if we start on this side of the graph, and we only take a few observations, we will determine it quickly or not quickly, what the mean is. Not quickly? Why not?
Wait, that's what we
Okay, I want to find the mean number of shoppers that go to Walmart, or sorry, to Costco or to Stater Bros. How many people are in front of me? If I take like 10 observations of that number, do I find the mean quickly in 10 observations? Yeah, kind of. When you look at it, like that is basically the same distribution as this one is here, right? So you don't really get more confident in time. Okay, you find out that number basically doesn't change. Okay, this one here, maybe even the same thing, but maybe takes a little longer because the spread is longer. Right? Spread is smaller, you get closer to the mean quicker, right? Okay. Another way to conceptualize this is the idea of what are the sources of our uncertainty. So there is what we call random uncertainty. We've just seen that, right? It's just going to have random other people in front of us, right? But we haven't really talked about the fact that we are taking an observation in real life. And so there's two sources of uncertainty. There's random. And human error will go under random, actually. You may remember this from computational.
that one.
Decimals?
Yeah.
Oh, that would be approximation error. Maybe. We'll talk about that in a second. Systematic. Okay, so here's the idea. We have discussed random errors. Errors in your observation that are natural to the cycle. There is a Poisson process. This process is characterized by some randomness. You roll the die, and God makes people in front of you, right? That's the idea. Okay. So there's ones that are built in. We can average them, and we can get closer to the mean. Then there are systematic uncertainties. And these systematic uncertainties are things that you're perhaps not as familiar with, but they are going to impact your ability to make an observation. Okay. So if you're, some people wear glasses here, okay? Let's say you walk into the grocery store and you forgot your glasses. Now, I have not changed the physical setup at all. The Poisson process is still being undertaken. The same number of people are in front of us. But I personally have horrible nearsightedness. Horrible. I can see to about here safely. Okay, for folks online, that's about here. Okay, and after that, it's mostly a blur. So now I show up, and instead of seeing 5 people in front of me, I see 3 or 4 shapes. Okay, so what's happened? The random uncertainty hasn't changed. But now my observations have a systematic error in them. And we have to characterize that with an uncertainty. So I could say, well, as soon as I take off my glasses, this adds plus minus 2 people to my observation. Okay. So now I go and I take observations over and over and over, but I always forget my glasses because I don't put them around my neck. If I now take the average, can I ignore that systematic uncertainty? Raise your hand for no. Raise your hand for yes. Raise your hand for the question again. Okay.
No.
All right, so let's think about this. My glasses are on. I go and make the observations. I have only the uncertainty due to the fact that it's a Poisson process. Okay. And I go and I make maybe 20 observations. I get a number. I take the average. I have some confidence in that average. Good. Then I do it again. But this time I keep forgetting my glasses. For 20 times, I don't bring my glasses. And I assign to myself an uncertainty of plus minus 2 humans. Okay. Will repeated measurements make that systematic uncertainty go down or disappear?
It may go down.
May it go down? Raise your hand for it may go down. Raise your hand for it won't go down. Raise your hand for no thank you. Raise your hand for I lost my hands. Okay, so it won't go down. You are stuck with that uncertainty. And that's the major source of difficulty that we're going to run into here. Okay. The systematic uncertainties can't be averaged away because they're present in every single observation. So let's assume that I am off by 2 people. I'm overcounting by 2 people, but I do it to every group. Now my mean has moved up by 2 for every single group of people, but it doesn't represent the true mean, right? I don't know which way I'm off. I could be counting too many people. I could be counting too little people. I just don't know. So now I've introduced new uncertainty into my confidence, right? I'm less confident by about 2 people. Does that make sense? Okay. I know these are all very abstract concepts. That's why I'm trying to do them with people. If they make less sense to you, I apologize. So we could try something else. Okay. Okay. So let's take a break from thinking really hard about numbers and math. And let's pull out our personal statements. You have personal statements, I hope? Okay. And we're going to peer review them in the opposite direction this time. We'll just take like 15 minutes to read one of those personal statements. And then we're going to jump into the data analysis software that I showed 2 weeks ago. And we'll look at some of the observations that were taken last Tuesday. We won't go up to the observatory tonight because we have an open house tomorrow and the next night. So if you want to go take more observations, I would encourage you to do that either of those 2 nights. You're welcome to. Okay. And then for folks who are not doing the observations, I ask you to write up something about what you are doing. So I'll need weekly updates. Okay.
Dr. Griswani?
You know, you need someone to start doing stuff with you, let me know, because I know Kim, Dr. Kim was interested.
Dr. Griswani?
Is there another Kim? Oh, sorry, yeah. It's Katie. Okay. What was the question?
I I sent you my CV. Can I do something with that, or should I just send John my
Yeah.
personal statement?
Yeah, no, you can certainly do it with that. And
Okay.
I think you can both give one another feedback. We're still just thinking about it in the context of what is good writing. Are we communicating with good topic sentence, etc. Right?
Okay. I think I'll just send my personal statement to John, and then I'll kind of do my CV more with you so that John can get some more. Yeah. Okay. Perfect. Thank you.
Sounds good to me.
So which way did we pass it last? Because I know I fucked this up last time. Okay, so you hand it to Reed, I believe, right? You handed it in the past or right now?
Oh, yeah.
Yeah, so we're doing the opposite direction so we can get new feedback. Did you say good luck?
Yeah.
John, do you want to join the Astro?
We can also, I can create a breakout room for you both if you want to chat.
Yeah, actually, that's good. We were gonna do
Yeah, that could work. I was gonna message him over Slack.
Okay, so let me just open this up right here and you can jump in if you'd like.
Deal. Thanks.
Yep. So you're peer reviewing. So what you're doing is you're looking at someone else's reading and you are giving them feedback on their topic sentences. You're giving them feedback on their structure. You're not really making them feel bad, right? You're not saying, hey, this is a shitty sentence. You're saying, I think it could be better if you tried XYZ. Or if you notice a typo or an edit, you can point that out as well. Remember that we used a rubric. We created a rubric together of what was good and bad scientific writing, right? So we're going to reference that. That's what we're focusing on. We're looking for, is it concise? Is it generally sound professional, etc. Right? And if you need that rubric, I think it's in the group chat, the Slack one. Yeah. Yes, it's for us. You don't just write that on everything? Oh. Really? Oh, I guess that makes kind of sense. I don't even know the names half the time. That's fair. That's fair.
I don't think it's in the astronomy. Observations, you know.
Oh, you're right. Okay, hold on. Let me pull it up.
I'm gonna.
Okay, so let me drop it in the chat right now. Oh, right, because this is when my computer was turning itself off, remember? You were not there, maybe.
So last week.
2 weeks ago. And it was like going through a mandated restart and then. Okay. You didn't say that, right? Okay. So hopefully the feedback that you're giving is centered around the rubric that we were using, right? And so we're hoping to point people towards better topic sentences, better paragraph structure, right? Do the paragraph sentences after the topic sentence support that topic sentence, or should they be somewhere else, etc., right? And then we can look at grammar and everything else later on. Okay. So instead, I want to talk a little bit about, I'm going to share my other screen here, desktop 2. I'm going to talk a little bit about, I hope they can see this good. Just launch. That was working. I guess. So I showed you this IPython notebook, right? And people were like, ugh, fucking hate Python, right? But we're going to try to use some of the concepts that we've been talking about, in particular, with respect to how we would begin to characterize any of these observations. So let's say you have data in hand. And let's do this. All right, there we go. Okay. So if you're not using EV scopes, this might sound boring to you. We'll talk a little bit about systematic uncertainties and non-systematic uncertainties, but generally speaking, this is the type of analysis that I'll expect from you. You're going to load the data in, whatever it is, you know, whether it's a spreadsheet that you tabulated your values, and you're going to make estimations of your uncertainty. So we talked a little bit about how we would determine signal to noise, and throughout the course of the next few weeks, we will talk about whether or not we need to characterize that noise in a more meaningful way for whatever your specific observations are. So while we'll talk about observational ASTR right now, you know, think about it in the back of your mind. Is there uncertainty in my detector? Is there uncertainty in the wind speed of my fan? Is there uncertainty in the thickness of the wheels that I'm using, right? Whatever your particular product is. Does that make sense? Okay. So you remember this? Has anyone opened it? I think it's so sad sometimes. Okay, so let's make it bigger. Sorry, I know this is not ideal. I should have grabbed the typey type. Okay, so let's go through. You want to load all this stuff in. It's probably got more stuff than you need, but that's okay. Here's the file destination. You want to change this to whatever your downloads are. So if you pulled this data off the EV scope, it's going to look like that. Now you'll notice some interesting things now that you've used the EV scope, right? You'll notice that it has a date. Last time I taught this class was correct. And what time of the year? January. And what date was this observation taken? Correct. And then what does this thing say? That is the time, correct. So it's built right into the file name. So if you were keeping detailed notes, which I believe everyone was, and you had some time periods for when you took this data or that data, it's built right in, right into the file name. Okay. Okay. So let's look at that one. You can just load it right in. Pretty cool, right? So there it is. And I asked for some image information. So for folks who want to remember their Python, here's the image. Oh, let me walk you through the different pieces here. I'll do it with my. Okay. So for folks online, you can read, this is the file destination. So this is the file path. Users, my username. Now note this is on a Mac. So if you're using a PC, it will be different. There'll be backslashes, just like we saw with CoCalc. Okay. Downloads is where I put this file. You can put it wherever you want. Some people will make a folder with all of these observations, and that way they can access them one after the other after the other. And then this is what's changing, right? If you want, I can show you how to use either glob or OS, the operating system. And essentially what that's going to do, you say, you know, glob inside this file. I know it sounds silly, but this is a real Python code. And what it does is it looks inside the folder and it tells you what all the file names are. So instead of going in and by hand clicking every single name, right, from your notes, which you're not going to be able to do, you just glob the file list and then it shows up and you can go, you know, glob 1, glob 2, glob 3. That makes sense? It's not really that easy, but I'm making it that easier for the purpose of this conversation. Okay. So now you have the file in hand and you downloaded it. Okay. What do you see? Stars, great. Okay, that's where we want to start. So at least we know that we took an observation that was meaningful. There's some stars here. There's some stars here. There's no stars in this region. Is that scary? Well, did the camera pick it up? That's a very good question. Okay, so you may have seen this very funny meme. Okay. If camera circle, why picture square? Very good question that I don't know the answer to. Here, let me download the other one. I might have messed up the names. Yeah, it's a very good question. I don't know why the dates are messed up here. Maybe this is universal time and this is real time. Okay, something to keep in mind that Isabel noticed. Good eyes. Your date might not match. So note here that it says January 7th, 2021. So it very well could be the case that when I took these observations, this is working on universal time. And this is the time that's local on my phone, or vice versa. This is the local time, and this is the universal time that was taken. So we want to pay attention to that when we download the first file. Look at what it says on the timescale. So you probably will have two of these, actually. And it's not that there are no stars here. This is a vignette. So that means like sometimes you've seen like old-timey photos and they put like a white border around it, right? And it like doesn't show you the edges. That's a chemical treating process. They like literally do that. Okay. This is a mask. This is a physical set everything equal to black that the computer does. But you should have two versions. So inside of your EV scope settings, you can say download without this annoying thing, please. And it'll give you the entire square, just like you would on your phone. And so you say to yourself, well, why circle makes square picture? Right? That's what everyone asks themselves at the end of the day. And why is picture square? The question is if the telescope is circular, why is the picture not circular? Because the CCD is a rectangle. Okay. So in practice, it's really important to remember. Okay. So in practice, it's really important to remember that we have something that has a lens like this. And let's say we have a picture of a tree, a canonical picture of a tree. Wow, that's a really good tree, Prismani. Are you an artist? Did you go to art school? Okay. And what happens when it goes through the lens? It flips and usually magnifies, right? So let's assume that I did that super good. Here I'm going to make it really small. So let's say this is the part that is space. Okay, so this is space outside. And this is the CCD inside. Okay. This shape projects all of this here. Right? Do I get the whole picture of outside? No. I get the section that is the size of my CCD. If I had a bigger CCD, I'd get a bigger picture. Okay. Okay. Usually what you end up having is you have a CCD and it'll be mounted like this. And this is like the front of it. And those are all the CCD panels on it. They're all collecting light. And then around it, you have all the wires. and the wires go off. And so then the light just goes, hits those places and it doesn't do anything. Okay. Okay, so you want to download the unvignetted one that gives you the full image and you can zoom in and you can do whatever you want there. Okay. You'll notice the last piece I said here is it says print image MP shape. What does that mean again? How many pixels is this? A 1,120 by 1,120 by. Yeah, why 4? That's so strange. I did take 4 pictures, but in this particular CCD, okay, and this is not the case for the ones that we would use in the big telescopes. If this is, if this is my CCD, and I think about this as a typical pixel size, the way that we do this in our modern electronics is to actually cut this up into 4 pieces. And this one is sensitive to red light. This one is sensitive to green light. This one is sensitive to blue light. And this, oh, that's a D. So, and then this one is sensitive to the infrared. In your camera, in your phone, you'll notice that you can look for your TV while it's off, because your TV is emitting a little red blinking light. Cameras do this too, right? They sense the world around them by taking in infrared light. And so your phone can use that infrared information, the heat, more or less, to build low light photos. You know how your phone can sometimes see better than you at night? That's that 4th channel. And then what they do is they just map that information into the visual. Okay. Okay. So let's look at our channels. So here are 0, 1, 2. We remember that when we are accessing data, it starts at 0. And I'm saying, give me all of the pixels. Okay. And you can use some horrible color choices here if you want, or you could use reasonable ones. I'm just showing you a variety. Here's tab 20G. And here's the same image. Remember, this is an image of Orion's nebula, or a nebula in Orion. And this one here is, I forget what order they are. I think this is blue. This is green. Oh, no, other way around. This is red. This is green. And this is blue. And then I took the difference between them. And the difference between them tells me where the blue is in the image. So did I do it right? Well, there's blue in this piece and there's red in this piece. Okay, let's look. Oops. Yeah, there's blue in this piece and there's red in this piece. Genius, let's go. Right? Amazing. So now we can do analysis of the images, right? And we saw this before, that if you look in the background here, it looks pretty black, right? Looks like there's nothing there. Is there nothing there? There is stuff there. And what is in that dark stuff? Are there stars? Far, far. Okay, yeah, that's true. There's probably very distant stars. You're always right that if you're pointing somewhere, you're looking at a star. But what is the main source of light in the places that are dark? So let me show you a different example. If I scroll all the way down, okay, we zoom in on a star. Here's an image, red, green, blue. And there's all this stuff in the background when I do the color difference. What is this? Scattered light, right? And so what are the reasons why it's scattered? Who's scattering it? The atmosphere is scattering it. Very good. And we can add on to it the fact that we talked about some of the examples today. So atmosphere is doing some scattering. Good. Twinkling, right? What's that? Well, the star scatter is going to be mostly confined to the star. So if we look in this region, there's no reason to expect that it would be dominated by the star. Yeah, light pollution. So that would be the same type of scattering here, right? That would be what we call sky background. We're going to take both of those thoughts. We're going to add them together into something that we call the sky background term. Basically says that if I take the average in this region, I will end up with light. I should end up with no light, right? That part of space looks black to me, just like this picture. But if I look at the data, it looks like non-zero. Okay, so what I'm going to do, if I want to calculate the brightness here, I have to take away the average here and assume that the background is mostly the same, and therefore I don't overestimate this one. Does that make sense? Yeah.
So. I think it's a dumb question, but if you take a picture in space, you not have that.
Aha, very good question. Raise your hand for will it still be there? Raise your hand for it won't be there. Raise your hand for I don't like questions. Okay, it won't be there. There will be something else there. So this is a combination of effects, but the scattering from the sun or from the atmosphere will be gone. And you get much better background. That's why we send stuff to space. Not only to see different wavelengths of light that we can't see at the surface, but also to get very sharp resolutions because you get less diffraction around the object and you can get to deeper parts of the background, right? So you can see fainter things. Okay, so we didn't really talk about this in a lot of detail, but there's another problem here in this region and in everywhere else. The beginning of our observations, we take a dark frame, and that is to characterize the detector itself. So the way that I want you to think about this detector is that physically, it's a lot like a bucket. Okay. It's a very special bucket. Okay. So photons comes in. Okay, that's a photon symbol. And it catches all these photons. And it collects the photons, and photons, as you are about to learn in ENM2, are charge. Okay. So they are going to add electrons here at the bottom of the potential well. Okay. And they're gonna generate a potential difference from here to here. Okay. And essentially what the CCD is gonna do, gonna collect all these photons, some potential is gonna build up right here, and then you're gonna read it out. Okay. So that essentially just means that you ask each bin, you say, what was the potential difference there? That's the one that you can measure, the electronic one. And then you divide it by how many photons you think you got. And that tells you how many you originally think you had, right? Well, there's one problem. And that is that electrons that are just sitting here, okay? Sometimes it's hot. And they're just like living their best lives. And they just say, well, I just want to be here. And they just jump on their own. And they don't need light to do it. Okay. So sometimes that happens more when it's hot. Make sense? So essentially what you're looking at here, this is basically a form of background dark that we need to subtract off. And every pixel is going to be sensitive to this. So each one of the pixels is temperature independent. Some of them are more sensitive to heat on a given day. Fucking knows why. Some of them are less. Okay. Sometimes you end up with a bad pixel. You may see this on your phone. You may see this on a screen. Sometimes you get like a green pixel that never goes away. You ever see that before? Yeah. So that pixel is just shot, right? It's sort of the reverse process. So when you think about a screen, it's the opposite of this. This is a CCD. It collects light and turns it into photons. Oh, sorry. It collects photons and turns them into numbers that we can read out on a screen. Those numbers are the result of something called the digital unit, which is a representation of a potential difference. Okay. But if you reverse this process, that's how you get LEDs. So essentially all you have to say is, hey, I'm going to send you some information. Specifically, I'm going to send you a certain amount of potential difference, and you make photons of that color, please. Okay, so how does your screen at home work, or how does your brand new LED work? Well, it works like this. You have a red, green, blue. Okay, and it tells you, okay, 40 red photons, please, and 100 green photons, and no blue photons. And then your eye goes, oh, I see like a reddish green color. Does that make sense? It's the same process back and forth. The only problem is that sometimes this little band junction gets fucked up. Okay. And we have to understand that, the hotter it is, the more likely it is that this connection won't work. So one of the other benefits, of course, to going to space is that it's cold in space. Great. So this type of technology works even better. And if you really want to do this type of technology like JWST does, they're looking at infrared light, which is the light of heat. So you have to be much colder than the light of heat, right? For X-ray detectors, do you have to cool them down a lot? Actually, surprisingly, not really. Because the energy from an X-ray is so large, then you don't often have that type of energy jumping. So you're creating basically what's called a band gap here. And this is going to be energy dependent. Every time that I get a photon, I'm going to jump from here to here. That makes sense? I didn't explain this bucket very well. But basically, you have a bucket. You have electrons all at the bottom. Each one of them, when they take in one photon, they jump from the top to the bottom. And you just collect the number of electrons at the bottom. Okay? So if I take in an X-ray photon, that usually means I can jump really far because they're super energetic. So I can make this band gap really big. And usually thermal doesn't do that as well. So UV spectrometers are sometimes on something called a CMOS detector. It's a different type of detector, and it uses an amplifier to turn one ultraviolet photon into a bunch of visible photons. And then the same technology occurs. Make sense? Okay. So this is a source of noise that we call dark current or dark noise. And you won't always win there either. The nice thing about dark current and dark noise is it is random. Okay. So unless you took a bad dark frame, you should be able to average this out because the number of photons coming in, random, the number of electrons jumping is 1-to-1 with that. And if you add in any thermal noise of them just spontaneously jumping, that's also random. So we have two random processes added together, still random, right? Okay, and random processes, we can tamp down the noise with additional observations. Systematic processes, we cannot. Does that make sense? Okay, do we need a break, 15-minute break before we start jumping into how to do the data analysis, or do you want to just finish this out? Well, so I want to just talk about the data that you have in hand and how you're going to attack it. I mean, we've all talked this through before. So this is recorded and you can go back and watch it if you don't remember. I'm not going to walk through each step here, but you have a bunch of observations of the same thing. And two of the major things we were changing there were exposure time and the gain. And one of the first things you want to do is you want to look at each one of those images and put them here into this type of a format. The reason for that is you are going to see this on the background. Okay, we just talked about these sources of background. Do you have better or worse background from the sky and from dark current when your exposure is longer or shorter? Do you have better background when your gain is higher or lower? right? That's the first investigation. Does this flatten out at higher gain or lower gain? Does it flatten out at higher exposure or lower exposure, right? These are the questions that you're asking yourself. So you're going to go through and you're going to grab all those different ones. And notice that I made it better. How did I make it better in this image? You don't know. Oh, you're going to find out for yourself, right? So you have to make sure that you do this before you go back up. It won't take very long, okay? You just add in all your photos. You go down to this piece. You go one by one and you create a little table. You say, looked good here, look good here, look shitty here, look shitty here, look good here, look good, look here, shitty, right? And so as you go through that process, you'll see in this group of observations, which ones looked better and which ones looked worse. And then when you go back up, you can use the better settings, not the worst settings. Because if you go up, you take a whole bunch of observations and all of them are unusable because they're all saturated, you haven't learned anything, have you? Right? We want to learn stuff. We want to do like great science. Okay. Okay. Now do we want to take a break or are we done? You want me to talk for a half an hour? Oh, okay. So my plan was not to come back in for me to keep talking, right? My plan was for me to come back and for you to do this. I need from the people who are not doing observational, I need for them to turn in what they've been doing. I need for the people who are doing observational to do this. So I know I'm just talking about it now, but you know, grab those files out, start this analysis, break it up into teams. One group of person does this, one group of person does that, right? Because you have 2 sets of observations that you can do tomorrow. Or sorry, two days of observations that start tomorrow. So not even if your whole team goes up, maybe 1 or 2 people go up, send them up there with better parameters, right? That's what I'm asking for today.
Dr. Krismani, we just came back into the Zoom. We didn't know if you were gonna close the breakout room or not.
Oh, sorry. No, I should have contacted you, but that's my bad. Hold on, let me go back here. Stop the share. At the end of this, you can watch the recording. It's only like 20 minutes. I think we stopped at 5. Is that right? Something like that. Okay, so what right now we're debating. John, who's online? Yeah. Okay, so John, you did observations with us.
Yes, my partner is, I think, not in class right now. Jose.
Okay. So just see if you can contact anyone else in those other groups that you were with, because we're gonna do some data analysis using the astrometry Python notebook.
Okay.
And Paolo, if you're available, I believe Kobe and Andres are here. They could talk to you. Is that no? Oh,
Like off camera.
Saying right now.
Yeah, so talk to them about what I just told you about, right? Which is getting status reports every week and seeing where we are, right? Because we can't, I mean, semester's almost done. You say thank God? Okay, folks. I'll leave the room open if you want, but I'm gonna stop recording now.